Good day, everyone. I'm Bastian with Unisense Environment. Welcome to our webinar on leading process performance with nitrous oxide monitoring. We will look today into the various applications of using nitrous oxide measurements in wastewater treatment. First of all, I'd like to say thanks for the Danish Water Technology Alliance and the US Water Alliance for powering this webinar, supporting us with the outreach. We have almost 400 people signed up to this webinar, so really great to see the global interest in the topic, and we have seen it climb steadily over the last 4 years since we've been doing these webinars. So it's really fantastic that so many are interested and are joining us here today. Before going into the depth of the program, I'd just like to make a few announcements. The first is about our LinkedIn profile. We do post a lot of similar events that we're holding and any other studies that we're involved in on our LinkedIn profile. So I do invite you to use that QR code. If you're not following us already, you can do it right now on your phone. And then I would like to highlight that our management is actually on a North America tour from in the next week. First of all, on September 25, they will be in Toronto, where they're joining a webinar, a seminar organized by our Ontario distributor Aquify, hosted together with region of Halton at Mid-Halton Wastewater Treatment Plant. So thanks a lot for them for making this possible. And then they will be present at WEFTEC on the other side of the border in Chicago, just for the whole WEFTEC at our booth. If you like to connect already now and make sure that you catch them, feel free to reach out and drop us we can make sure that you have a time slot for you at the booth, and we look forward to welcome you there. Then going into the program for today, we have some fantastic speakers who are so generous with their time and have made the preparations for this talk, and are willing to share their experience. So I'd like to just give them a quick introduction. Chandra Baker from Halton region is going to present together with Amber Klassen from Aquify, and they will give us a more practical introduction into the use of nitrous oxide sensors and how they are applied as wastewater treatment plants. And then they will look deeper also into some ongoing measurement campaigns and the use of that data. And after that, we will take a deep dive into process optimization. This will be with Bishav Bhattarai from Black & Veatch in California, and Tyler Biese from New Water in Green Bay. And there we will focus specifically on low energy biological nitrogen removal applications. So very much looking forward to these two presentations. I will round off the presentations with some examples from Europe, and then we will close the webinar after 1.5 hours. Questions that do come up will you will be able to share them in the Q&A box. You should all have a little Q&A box at the top of your Teams window. So just drop the questions in there as they come up, also during the presentations, and I will moderate the questions afterwards, asking them directly to the presenters. So there's no need to wait with your questions or to ask them yourselves. You can just drop them in the Q&A. Fantastic. I think this is all I wanted to say. So we can start with the first presentation. Chandra and Amber, if you like to turn on your cameras and share your screen, and look very much forward to your presentation. I would say the floor is yours.
Okay, excellent. Hopefully everyone can hear and see me.
Yes, we hear you well.
And I will just share my screen. So thank you, Bastian, and good morning and welcome to everybody. We'll be going through the practical experiences, installing, moving, calibrating, and maintaining dissolved N2O sensors. Brief overview of what Chandra and I will be going over. We'll start with our introductions, move into a bit about the N2O sensor system, talk about calibration and maintenance, some installation considerations and mounting arrangements, and finally look at implementing the data for monitoring equipment in the Halton region. So, as Bastian mentioned, my name is Klassen. I am a professional engineer and a field service engineer at Aquify Water Technologies. We are a manufacturer and supplier of a myriad of water and wastewater treatment equipment in Ontario. And Chandra, if you'd like to go ahead.
Good morning, everyone. My name is Chandra Baker. I'm the superintendent of the Mid-Halton and North wastewater treatment plants at Halton Region. We're a municipality that fits between Toronto and Hamilton, just off of Lake Ontario. We have 6 operating wastewater facilities, and we will be discussing the N2O installations at our 2 largest.
So I'd like to start off this presentation by reminding us why it's important and why we're here and why we care. N2O accounts for as much as 90% of greenhouse gas emissions from wastewater treatment plants. N2O has a global warming potential of 273 times that higher than CO2. This means for us as an industry that it's really important to try to reduce our emissions of N2O to help significantly reduce our environmental impact. I really love the slogan from You to Sense, Measure to Know, because really knowing is the first step in understanding and then making a difference. So when talking about N2O and wastewater treatment plants, your primary contributors are going to be your activated sludge processes, such as aeration tanks, oxidation ditches, and biological reactors, as they utilize nitrifying and denitrifying bacteria to reduce ammonia, nitrates, and nitrites from the wastewater. N2O may also be produced in locations where N2O formation is a side production of N transformations under subideal pathways. N2O has multiple pathways in which production conditions can be met, and parameters such as oxygen availability, ammonia shock loading, temperature, and constituent concentrations can all influence N2O production. In Ontario, our installations of N2O sensors are typically placed at the influent to the aeration train and then near the effluent of the aeration train in the aerated and anoxic zones. These locations can vary and are typically selected based on an N2O profiling, which will be covered in a later slide. So no surprise, but the equipment I'll be speaking on specifically during this presentation is the Unisense Environment N2O sensor. This sensor is a real-time monitoring sensor that measures N2O in the liquid phase. The system is comprised of 3 main parts. This includes the controller, the sensor body, and the sensor head. Starting with the controller, this is an IP67 waterproof and dust-resistant cover that requires a 240-volt supply. You can connect up to 2 sensors at one time within a maximum distance of 100 meters from the controller. It can be connected to SCADA via a 4 to 20 milliamp signal, Modbus, or Profibus DP. And the data from the controller can be collected via PLC or SCADA and can be manually downloaded to a USB drive and uploaded to the Unisense software for data interpretation. For the HMI controller, the top value that you're seeing here is the calibrated concentration in milligrams of N2O per liter. And so the sensor takes and records a reading every 10 seconds to give you the full picture. The value below this is the temperature of the sample read by the sensor body. And below this is the raw percent value. Now, this number can be a little bit confusing, but this is the number that is the total percent of the maximum reading capacity. So in this value, I normally use it just to check on the sensor health. Below this is the airflow. And this can be done and connected to an airflow meter, and then we'll display it on your airflow box. The body of the sensor is a 44 millimeter aluminum alloy housing and a black POM acetyl copolymer. This is also where the temperature sensor is located. And as pictured before, there is an additional chain mount, and we strongly recommend you use this to help alleviate some of the strain on the controller cable, especially in areas where it's like incredibly turbulent or there's a more of a unique installation needs that will require a longer distance. You don't want the controller body just dangling off the controller cable. The sensor head is made up of a combination of glass, plastic, and metal, with the most prominent feature being the glass tip. Within the glass casing, a silicone membrane allows for N2O to pass through, And encased in the glass is an oxygen scavenging solution, which removes oxygen, allowing for the sensor to measure N2O with a series of anodic and cathodic reactions. The purpose of my presentation isn't really to get into the nitty-gritty of how this works, but there is an abundance of information on the Unisense website if you're interested. The key thing to note, though, is that the sensor does have a life of 6 months. The sensors come in a variety of working ranges to suit your specific applications. For most conventional facilities, the standard range sensor will be suitable. Moving on to calibration and maintenance. To complete the calibration, the first thing that you'll need is a calibration kit. And this includes solutions, syringes, and instructions to complete the calibration. What's pictured here is typically everything that we'll order for a 6-month 2-sensor replacement. The sensor does need to be calibrated every 2 months or plus or minus 3 degrees Celsius of temperature fluctuation, and then also after each sensor replacement. So on the left, the video that you're seeing there is what the HMI screen looks like once the sensor is placed into a calibration solution. It is important to record the calibration temperature, and you want to try to make sure that the temperature is the same as the process temperature, and this can be recorded in the controller HMI as well. Each calibration is then stored in the internal logbook and can be accessed at any time. It is also really important to make sure that the calibration or at the probe of the sensor is cleaned before each calibration. And this can be easily done using water and paper towel. The key thing to note is that you want to be careful around the glass tip of the sensor as it is fragile. A fun thing to note too is that the sensor can still do readings even if there is biofouling, as long as the tip of the sensor is exposed. And you can see this in the bottom left hand of my screen. Or bottom right hand, sorry, I apologize. Another important thing to note about cleaning is that you want to make sure that there's any excessive ragging is removed. Not only is this important to remove the ragging to protect the cabling, but it could also potentially cause damage to the sensor head if any of the ragging bits get caught up in the aluminum protection. And here's just pictured an example of what I would take to site to calibrate the Unisense sensors for a 2-sensor installation. Moving on to the installation, just some things to consider at a high level. Accessibility, like where is it going? You may need to consider coming up with a custom solution to reach your sample. Is there anything that you need to protect the sensor from? Wildlife can be very destructive, and you want to be able to protect your equipment as well as your people maintaining your equipment. Are there any obstacles restricting the access to the controller or the sensors? Is there space to perform calibration and maintenance, or is it a little bit tight? Do you have adequate power supply? And what is it that you're trying to achieve? Does the sensor need to move around, or are you trying to keep it in one spot? A few other things is process conditions. Is the flow really turbulent, or do you have floatables in the process that may require some additional configuration in order to keep everything in working order? Additionally, temperature, ambient process, and weather conditions, rain, snow, sun, ice, freezing, whatever it is, you want to make sure that your equipment is protected from the elements. And finally, your calibration requirements. Do you have what you need? Do you have clean tempered water that's at the temperature of your process, just to get the job done? Continue on with the installation considerations. The sensor body does need to be fully submerged, so whatever configuration that you use needs to be long enough to fully reach the wastewater. So the temperature sensor is located in that red box. The weight of the sensor, again, should be supported by the chain, not the cable. The sensor body should not be submerged, as there would be exposed electronics without the sensor head. And if you're using any additional electrical connections, such as an extension cable, you want to ensure that all of the cabling is free from strain and protected from the. You want to keep them dry and make sure that there's no pooling or puddling around where they're connecting. Just some examples of what we see here in Ontario for our fixed mounting arrangements. They can be as simple as the one on the left with just the unit strut into the sample, or as rigid as the one on the far right, which is in an MVR process, which is quite turbulent. Additionally, if you want to move the system, you can look at putting something like we have on the screen here, which is like a swivel. And this allows us to move the sensor out of the wastewater for the calibration or completely remove it for N2O profiling. And similarly, this one is more of a slide mechanism to slide the probe in and out to do any kind of maintenance or calibration. For the controllers, you can look at having something that is full access and has just a weather protection on it. Some of the downsides include getting just too much glare from the sun, but so far I haven't had many issues on site. If you are worried or you're in a bit more of a higher weather area, considering using an enclosed structure with a heater is also an option. Just keep in mind that you will still need to open the enclosure to access the panel and the HMI. So moving on to implementing data from the N2O sensors in the Halton region. As Chandra mentioned, the regional municipality of Halton is located in the Golden Horseshoe of Southern Ontario. It is comprised of the city of Burlington and towns of Oakville, Milton, and Halton Hills. There are a total of 6 wastewater treatment plants in the region, indicated by the blue markers. These plants deal with 232 cubic meters of wastewater every day. 2 of the 6 facilities currently have Unison's N2O monitoring in place. And this includes the Mid-Halton wastewater treatment plant and the Skyway wastewater treatment plant. And Chandra.
Thanks, Amber. You can go to the next slide.
Oh, perfect. Thank you.
All right, so at our 2 largest facilities, we have the N2O sensors set up. The pictures on the screen are of the Skyway facility. Go back one. Jumped over fast, Amber. Gotta go back one slide.
Sorry.
Maybe it's a bit of a delay. So as you can see, the facilities, we have the locations of the sensors at the beginning and end of the aeration zones. At the Mid-Halton plant, the first 2 passes are anoxic, with the second one being a swing zone. For the past year, we've been monitoring baseline data at both facilities, and that's swing zone at Mid-Halton has been active. So the locations in the beginning of the 3rd pass as the wastewater enters the aerobic zones. For Skyway, we don't have any anoxic zones, so the sensors are placed at the beginning and the end of the aeration basin. So over this past year, we've been doing a series of studies to measure the baseline data, as well as taking additional data to help us interpret what we're actually measuring. Part of that includes an N2O profiling, where we've gone through the aeration tanks, looking at different sample locations to determine the ideal locations for the N2O sensors. We're looking for hotspots, and during our study, we did this measurement 4 times throughout the year, as well as measuring our DO, our ammonia, nitrite, and TKN. This allows us to really understand what is happening with the nitrification, denitrification cycles, as well as understanding what may be influencing the data that we are collecting. Next slide.
That's me, and I helped.
Yes, and Amber very much was part of our whole nitrogen profiling, which we appreciated the help. So this is some of the data that we've seen from our study over the past year. The top right slide is our sensor 1. We both have the raw data as well as the clean data. The raw data did pick up a lot of the times we were doing calibrations or changes to adjust for temperature. So when we're analyzing the data, we want to make sure that what we're analyzing to determine what our true emission rate is that data has been cleaned and verified for any outliers. The second set of data is location number 2. So sensor number 1 is location 1, sensor 2 is location number 2. As you can note in this, that the emissions from sensor 2, which is the end of the tanks, is typically higher than what we're measuring at the front of the tanks. Seasonally, we're seeing variation, as well as daily we see variation. So having a online monitor where we're constantly collecting data will help us to determine what our true emissions factors are. Next slide, please. So one of the things we found very interesting between the two facilities, so our Mid-Halton plant, our signal was very consistent throughout the full year of our baseline study. We did not see that with our Skyway facility. And we started seeing some malfunctioning happening in October of 2024. And as you can see, there has been, through the data, there is a rising of the baseline data to the point that it actually malfunctions come November. What was determined to be the issue with both the signal and the failure is that the sensors became oxygen sensitive because of the high DO concentrations found at the Skyway facility. This facility does CEPT, so they are taking a lot of the carbon out in their primary influent. And when they reached the aeration zone, they're starting to nitrify almost immediately. So by the end of the aeration tank, they've consumed all their ammonia, leading to high DOs at the back end. And what this does is it causes the oxygen scavenging reagent to be consumed faster than usual. What we've done to correct that moving forward is we've actually used a custom sensor to allow us to measure those, the N2O, without removing the oxygen scavenging. There is a slight lower sensitivity, but we're getting a more consistent signal. So as you can see, with these sensors, go back.
Sorry, my bad.
So this data goes through after the sensors have been replaced with the new type of sensor. We are in fact getting a much better signal, and we also moved to a different tank. What we found, we had some malfunctions in the tank that they had been installed, and we moved it to a similar tank that we were able to get a much better signal for. So some of the things that we've learned over our baseline year of data is some of the correlations of what influences our nitrous oxide production. So as you can see from this correlations, these things change both seasonally as well as location. So the Mid-Halton plant, there's a large emphasis on our mixed liquor concentration, the DO, as well as the pH, both negatively and positively. We were able to see changes in how we created our process, and how that also fluctuates on how we see the nitrous oxide being consumed or not. Skyway, we actually had a period of inhibition in the November to December 2024. So you can definitely see that the strongly negative influence of the fact that we had some nitrification inhibition led to higher emission rates, as well as having the sensor probe go off. So a little bit of information there. So what we've done with this baseline data is, using these correlations, we've come up with some alternate testing strategies that we are currently underway at some of the facilities to determine if we're making any impact on the N2O emissions and what we're seeing. And we've had some positives so far, so we're going through our list of those baseline changes. So at this point, is there any questions for either Amber or myself?
Thank you very much, both of you, for the very insightful presentation. I think in order to keep the bandwidth running, it's a good idea to turn the lovely fish from the treatment plant out of the picture.
Yeah.
I know that. I like your points about wildlife as well. We have experience with rats being an issue at many plants as well, that can be harmful to any kinds of cable as well. So that's these are all things to look out for. I see there's a hand raised, David. I'm really sorry that we've turned off the ability to ask questions directly. So I would ask you to write down the question in the Q&A, and then I will read it out. We just had to do that because there were so many people on the call. But then I will read it out as we get there. I see there's two questions in the right now in the Q&A. The first one I think is mainly for me. Are you developing sensors that last longer than the 6 months? And well, I can say that we're definitely always working on improving our products. Right now, I can't promise anything in that direction, but we're constantly working on improvement of all our products. And it plays into the question, the other question, where we are asked, could you please elaborate on the fouling of the probes and the oxygen scouring efficiency? So maybe I can just elaborate shortly on the aging of the sensor. That is determined mainly by 3 factors. This is temperature, the amount of nitrous oxide that it sees, and the amount of oxygen that it sees. And this oxygen scouring, we know that it holds its lifetime up to a concentration of 10 milligrams per liter. So more than usual set point in a wastewater treatment plant would be. But under these high conditions, well, saturated oxygen conditions, then the sensor is getting overwhelmed, the standard range sensor, and then the switch to a customized high oxygen sensor was the right decision in this case. So I think, yeah, if you want to elaborate on that, but I think it just highlights that how very important it is that your data is being monitored instead of simply being taken in and recorded. So I think that
Sure,
that
yeah.
covers the point.
Yeah, I'm not sure. I can also touch a bit more on the like the fouling of the sensor, if you want to call it that. There is being in an aeration tank, there is a lot of biological activity that tends to grow on these sensors. But as I mentioned, as long as the tip of the sensor is exposed, you're always going to be getting an accurate reading. And just cleaning it off with a paper towel is more than sufficient. I find that when I go to facilities, even if it's been, the 2 months, I don't normally run into issues where there's excessive fouling. But if that's something that you're worried about at the facility, or if the readings again start acting funny or not what you're expecting to see, going out and cleaning the sensor is never a bad thing to do.
Mm-hmm. Yeah, as with any other equipment, I think in the wastewater treatment process, that's the case. We have some more questions. So Mikkel from Niras in Denmark is saying, great presentation, thanks, and asking, did you determine the predominant pathway responsible for production of nitrous oxide? I guess it's a question to you, Chandra, and also maybe I can add on to that, whether you are planning to look deeper into, well, the data analysis and learning from the different correlations that you have. Maybe you can elaborate a little bit on that.
Yeah, it really, again, it comes down to facility being specific facilities. So for Mid-Halton, that plant has an alkalinity deficiency where we are, in fact, dosing alkalinity to ensure that we have a sufficient pH and alkalinity in the system. And that is one of our drivers, that if that alkalinity drops too low, that we are, in fact, emitting more. Also, our ammonia loading to the facility is a huge driver, which we found in our data. We typically, because we have a Christmas shutdown, we tend to load ammonia from our side stream higher than we do typically during the year, and did notice the correlation between the ammonia loading to the facility with our nitrous oxide production. With regards to Skyway, obviously being able to see if your system is in fact either inhibited or having struggles. So if there's process issues with your facility, that also is a main driver for nitrous oxide emissions. The nice thing about having the sensor, it almost gives you a heads up that you're running into a potential process issue. So it really is a great indicator to know if your process is functioning as expected or if you're about to run into an upset.
Great, thanks for elaborating. We do have a lot of questions that ask into the DO. So I'm not sure if you actually know the concentration that you had been monitoring or measuring in the nights. I remember it was saturated. and more than
typically above 4 milligrams per liter. So I think it's above 4. Sometimes we were up into the 6-8 milligrams per liter.
8. Mm-hmm.
When we were measuring. So whereas Mid-Halton, we're typically keeping those numbers down at 2. So hence the difference in what we were seeing in the results for the data.
Mm-hmm. Great. And let me just see through the slides. There were a few questions that ask into reporting of emissions in kilograms of nitrogen per day versus the liquid concentration that you're measuring. So maybe as a last point, when I look at the time, if you could elaborate a little bit on the way how you're calculating the emissions from the liquid concentration.
Yeah, so for that, we're taking the data of what the Unisense probe is outputting and then also adding in our airflow, which we're able to create a calculation that provides us 8 kilograms of nitrous oxide emitted. I go through the calculation now, but I don't have it quite in front of me. We are working with a consultant who's able to help us with that calculation.
Mm-hmm. And from our end, there's of course also always support on that, and all the formulas that are needed are described and scientifically validated. I will get into that on my last presentation as well. Great. I think because we are running short on time, there's a few questions that we couldn't address, but we will make sure we will address them in the follow-up to the webinar, and we will send that to our participants. So yeah, with that, I'd like to thank you both very, very much for your presentations and for being there for the questions. Yeah, please stay on. I'm sure you will for the rest of the webinar. And then I would like to call up the next 2 speakers, Tyler and Bishav. If you could just please pop on your screens, and we can move over to your presentation.
Okay, thank you.
Cool. Awesome. Hello, everyone. I'm Bishav from Black & Veatch, and I'm presenting with Tyler from Newater, Wisconsin. And we're presenting on N2O mitigation in low energy BNR systems. So let's start with looking at this or examining this planetary boundary framework, which outlines the safe operating space for across 9 critical Earth system processes. And we can see that climate change and biogeochemical flows are already outside the limit, and it's something that's directly impacted by the operation of our wastewater treatment plants, let it be through the uses of energy or through the direct emissions such as nitrous oxide as well. So that's why in this study, we are presenting 2 case studies, which is highlighting the low energy BNR, which is basically low DO, and the corresponding nitrous oxide emissions through them. So just highlighting 2 studies. So Tyler will be talking about a full-scale installation of the Unisense nitrous oxide sensors in Newater, Wisconsin, where it's focused on low DO as well, and it's highlighting on the dissolved nitrous oxide measurement in the full-scale plant. And then following that, I'll be talking about an SBR, it's a batch system. It's a research project funded by the Department of Energy, where we're looking at low energy, low nutrient, low nitrous oxide BNR, and some of the interesting observations that we have seen in that study. So with that, I would like to hand over to Tyler, and I'll be taking care of the slides.
Thank you, Bishav. So yeah, my name is Tyler Biese. I'm with Newater, a public utility in Green Bay, Wisconsin, and we're currently at the tail end of a full-scale low DO demonstration project that started in early 2024. I'm just going to provide some background on the project and some preliminary results related to airflow, nitrogen removal, and N2O as it relates to the low DO operation. We haven't really dived deep yet into the data analysis as we're still ongoing the demonstration basin study, but sharing some preliminary results. Next slide, please. So project background, we did a facility plan a couple of years ago, and low DO operation was identified as a potential to save 20 to 30% airflow compared to a conventional DO. As you can see the two graphs on the right, conventional DO, our facility demand with airflow would be around 10,000 SCFM. The low DO operation had the potential to reduce that by 8 to 8,000 SCFM on an average basis. And along with airflow savings, potential for nitrogen removal improvements. We also added a mixed liquor recycle pump for nitrogen removal, but primarily for improvements to our settleability, final clarifier, performance capacity, just to see how that would impact our facility. And then we also wanted to evaluate some of the risks associated with low DO, kind of how would it impact our settleability or filamentous growth. Also, what kind of aeration control improvements would we need? So we're just kind of dipping our toes into that now, but more discussion on that item later on in our project, I guess, implementation for full scale. And then how would it impact phosphorus performance? Next slide, please. So at our existing facility in Green Bay, we have 4 existing 2,500 horsepower blowers that were installed in the 1970s. So they're pretty big units back when we had a lot more load than we do now. And so the minimum turn down is 25,000 CFM. And as I mentioned before, our demand was modeled at around 10,000 CFM. So putting a lot more air than our facility really needs. And so these bigger process blowers account for 23% of our facility's energy demand, around 775 kilowatt hours per month, or $750,000 per year in blower energy. So if we can reduce that by installing new blowers, that would be a huge energy savings for our facility. And the graph on the right just shows the airflow benchmark compared to other facilities. This is something Black & Veatch put together during facility plan just to show where our facility lies compared to others. And on the right there, it's our current operation, the tall gray bar, at around 600 SCFM per MGD. And with low DO, we could possibly go down to 400, which is comparable to some of the lower facilities benchmarked, which would be a pretty significant reduction for us. Next slide, please. And so the new blowers have a potential to reduce aeration energy to 220,000 kilowatt hours per month, or almost save $500,000 of energy per year, which would be about 16% of our facility's energy consumption. So a pretty big impact, and that's why we wanted to jump into the full scale demonstration just to see, before we convert the full facility to this operation configuration, just to see what are some of the challenges, benefits, just to kind of work it out on paper before going all in. Next slide, please. So this is what we call the south plant, just 2 aeration basins. The basins and clarifiers are completely separated from each other. So we were able to do a test and a control, keeping the ecology completely separate. And there's research ongoing around the low DO ecology is a little bit different than high DO ecology. And so keeping those ecologies separate was a pretty big part of this demonstration project. Next slide, please. And then this slide just demonstrates we installed the mixed liquor recycle pump in the low DO basin to convert from AO to A2O, just to see the impacts on nitrogen removal and also settleability performance. So we installed a submersible pump near the end of the basin, and the blue force main that brings the mixed liquor back to the front of the anoxic basin. Next slide, please. And in addition to the mixed liquor recycle pump, we also installed compressed gas mixing in the anaerobic and anoxic zones, just to try a different mixing system compared to our current one. And we also installed compressed gas mixing in our aerobic zones, as during the low DO process, low aeration demand times, like during the middle of the night when you don't have as much load coming in, there's concern that you don't have enough air to adequately mix the tank. So the compressed gas mixing system will kick on and provide that supplemental mixing, so you don't have solid settling in the basin that could cause operational issues. Next slide, please. So we installed the mixed liquor recycle pump, and as you can see in the top basin, which we call South Plant 1, that converted the system, the demonstration test basin, we call it, to a N2O process versus the control which is an AO process. So the control system we kept at the aeration at the historical set points operational, which is around 3 mg or 3 milligrams per liter of DO in the control basin. And in the test basin, we tried several different configurations of low DO. And so the low DO was basically implemented in what is labeled as SC3, SC2, and SC1. So those are the low DO zones of the basin. And then at the end, we have a fixed aerobic zone, which is a constant higher DO to kind of maintain clarifier performance and also polish ammonia for effluent reasons. So that fixed aerobic zone DO is, depending on the time of the study, between 3 and 1.5. Next slide, please. So the objectives, after all these improvements, we kind of we're able to start up the low DO basin, and we just wanted to determine energy savings, effluent performance, just what it was like to control at a low DO, impacts of that configuration. And we also installed the N2O sensors in 2 of the aerobic subzones, subzone 1 and subzone 2. Next slide, please. This just shows a schedule of our low DO timeline. So there was almost a 6-month period of we transitioned down to the lower DO set points. We had a gradual reduction. We didn't just flip the switch and go from 3 to 0.5, potentially upsetting the microbiology and causing issues. So we gradually stepped it down. I think each month we kind of stepped it down a little bit more to give the bacteria time to acclimate to the new environment. In the second phase, we had a constant DO. Essentially, the first 3 subzones were kept at a constant DO. And then the third phase was going to a flex zone control, which is it's a control that Enviromix developed that changes the DO set point in the first 3 zones based on your loading. So essentially the airflow demand in the fixed aerobic zone is used to control the DO set points in the first 3 subzones. So when you have a higher airflow in the fixed aerobic, you have a higher loading to the facility. So the DO in those first 3 subzones will ramp up. When you have a lower fixed aerobic zone, aeration demand lower during lower loading times, and the DO in the first 3 subzones set point will be controlled to lower set point. Next slide, please. On the bottom left, this just shows a graph of the DO set points for the 4 grids, essentially. The first 3 grid, which is grid 1, grid 2, and I guess grids 3 and 4, were the same, starting at 3, which is the same set points as the control basin. And then they were gradually ramped down from 1.5, and we got all the way down to 0.3 as our lowest DO set point in September 2024. Next slide, please. This graph shows DO versus a typical diurnal period. So we have low loading during the morning hours and higher loading kind of during the early evening. And as such, the flex zone controller will vary the DO set points accordingly based on loading. Next slide, please. So this is a graph of aeration airflow reduction in the control basin versus the low DO test basin. So we had that transition period and the low DO, the constant low DO period, and then the flex zone period. And it's pretty highly variable based on influent loads and what's going on at the facility as far as equipment control. You know, we had some malfunctions with valves and things. So, but generally overall, the aeration savings in the low DO basin was around 22% averaged for the period. Next slide, please. This graph covers nitrogen removal, or sorry, nitrate removal in the test basin, which is in blue, versus the conventional DO basin, which is in gray. So the lower effluent nitrate possibly contributed to by the mixed liquid recycle pump, in addition to the low DO operation. So you can see it's 2 to 4 parts per million lower in the test basin due to the improvements. Next slide, please. This last slide has some results from the N2O probes we installed. The green graph on the left is from the results from subzone 1, and the blue on the right is the graph from subzone 2. As you can see, when we first installed the DO probe back in April of 2024, the N2O production was pretty low. And then we began to transition down, step down the DO, possibly, and then that caused spikes in the N2O, especially in the front of the basin, possibly due to shifts in ecology and a little bit of an upset there. But as you can see, as we got into flex zone, it stabilized and it went pretty low again, possibly due to acclimation of the low DO ecology in the system. Next slide, please.
Cool. Thanks, Tyler. All right, so we'll switch into another project, which is like a pilot scale sequencing batch reactors. And as I mentioned earlier, it's a project funded by the Department of Energy. So just a quick overview. I'll try to keep it short. Like, it's a pilot located at the city of Hayward in the San Francisco Bay Area here in California. And it's pretty standard, like 100-gallon SPR reactors equipped with all these pH, ORP, ammonium nitrate sensors, and along with that, more importantly, we have like the liquid Unisense N2O sensor as well. So we operated this SPR in a cyclic aeration pattern, as you can see on the top left, like an anoxic aerobic cyclic aeration. And we are treating a trickling filter effluent, which is low in carbon. So we are adding supplemental carbon at the start of 3 anoxic phases, as you can see with that arrows. And during this time, we tested with like 2 different types of carbon sources, and I'm going to talk about that later in the slides. Yeah, so the 2 carbon sources were like Micro C, which is glycerol-based Micro C 2000, and synthetic fermented, which is basically a cocktail of different VFAs based on some of the fermentation tests that we have been running in the same plant as well. And we operated with a low C2N dosing, not the wastewater influent, but low C2N dosing in those respective anoxic phases. So before we go into the nitrous oxide, let's look at the inorganic nitrogen species profiles. Yeah, so we have like ammonium nitrate and nitrite, pretty standard, like you're getting like nitrification in aerobic, and then denitrification occurring in the anoxic phases. So a couple of key takeaways were like there was no impacts on like nitrification, like we were getting full nitrification every time. The denite rates, we observed like the synthetic fermented was showing like a higher rate, denitrification rates. And in terms of the accumulation of nitrite, with both carbon sources, we were seeing nitrite accumulation as well. And just to kind of highlight, like a lot of studies, they have identified like nitrite accumulation as a trigger for nitrous oxide production as well. So, we were curious what the nitrous oxide profile looked like as well. So I'm going to show a general plot, like through our experiments, like highlighted by these three different colors, which is the golden color being with micro C and the blue and the green being with synthetic fermented with like low dosing and high dosing respectively. We were observing the anoxic production. So at the start of the anoxic phase, when we added carbon, we saw the liquid nitrous oxide concentration increased. And then when the aeration started, like we were seeing that dropping down, like the nitrous oxide concentration dropping down. And this was pretty consistent with over a year of pilot operation. This is a trend that we've been seeing throughout. So this highlights that although we were operating our SPR in the aerobic zones at low DO, like we were not seeing the increase in nitrous oxide concentration, which would, there might be some stripping there as well, but like at least with the nitrous oxide sensor, we weren't seeing any production detected in those aerobic zones. Now, like looking into like the comparison between different carbon sources, we saw that I'm just gonna one step back, so whatever the highest concentration of nitrous oxide there was, we observed at the end of the anoxic phase. We looked into that in like months of data and saw that micro C, we were seeing significantly higher nitrous oxide, which was being accumulated in the liquid phase. And that's when it goes to the aerobic phase, that was getting stripped out. So we were seeing a little bit higher risk using micro C as the carbon source in terms of nitrous oxide production and subsequently the emission as well. So if we are taking a closer look at it, like I've splitted this plots into three different graphs, like top being micro C, synthetic fermented in the middle one, and the higher dosing with synthetic fermented. And the carbon was being added at the locations highlighted by those red arrows. So we see that before the carbon is added, so the air stops and there is a couple of minutes lag between the carbon dose happens. We always see like some nitrous oxide production. Now, like it might be either, those nitrous oxide was getting stripped off and that stopped, or it's a transition between the aerobic and the anoxic where we were seeing that blip of nitrous oxide. But interesting thing was, as soon as you added carbon, like in micro C, the liquid nitrous oxide concentration started increasing from there. So you can see there's a slight change in slope as well. So you were seeing nitrous oxide creep up after that. While in case of synthetic fermented, we were seeing that nitrous oxide being uptaken. And either if you have like low carbon, it kind of like increased after a certain time, as you can see in this, I don't know if I can see my pointer out here, or like if you have sufficient carbon, like we didn't see any nitrous oxide through the anoxic phase, meaning like if you dose your carbon properly, like with the right type of carbon, like there's less likely that your nitrous oxide is getting stripped off in the subsequent aerobic phases. So we took a deep dive into it, and then we looked into like in situ denite testing because we didn't have like a benchtop N2O sensor. So we stopped the reactors and then tested with different C/N ratios and how does that impact nitrous oxide profile. And these two plots out here, we were seeing pretty, again, consistent trends throughout with multiple runs of experiments that always like there is significantly higher accumulation of nitrous oxide when using micro C, while in case of synthetic fermented, we were not seeing as high. And highlighting like, synthetic fermented as a carbon source, it has higher affinity towards nitrous oxide consumption possibly. And another thing to highlight here is, although we were observing nitrite accumulation in all these cases, the nitrous oxide doesn't necessarily mean that it will take place. So, like especially with some pDNA works that's, kind of like coming into play, and some concerns surrounding like nitrous oxide emissions, like our study shows that synthetic fermented doesn't lead to that high of a nitrous oxide production. So yeah, those were some observations there. And yeah, this just highlights, as we are increasing our carbon to NOx ratio, we were seeing improved or like increasing denite activity, but at the same time, that delta between nitrate and nitrite reduction, that was leading to higher nitrous oxide accumulation with micro C. But with synthetic fermented, we were just seeing that for a brief period, but that's not like, so this line might be deceiving, but like we're not seeing that going throughout the anoxic phase. So synthetic fermented showed like it posed less risk towards nitrous oxide accumulation. So now we are digging into why is this happening. So we are looking into whether that's because of the pDNA mechanism, like the differential rates, or it's like a truncated pathway of the denitrifiers when using micro C. So that's a question. So we are digging into that right now. And I don't know if I had that, but like some of the things that we're looking into, or like, yeah, to conclude, we observed that our low DO aerobic zone, we had a question like whether that's a big red flag in terms of nitrous oxide, but like looking into our aerobic zones nitrous oxide profile, we don't see that low DO is a hotspot, basically. The carbon type does influence based on what kind of nitrous oxide profile we would see in our reactors. And the C2N or the CO2 to NOx does as well. It's just finding the right carbon type and dosing to make sure like we mitigate the nitrous oxide through our systems. So some of the future works, which are some ongoing works we're doing, is looking at microbial ecology. Like, so we'll start with 16S, which will just show us the community profiles, but we're thinking of doing some RNA gene expression analysis as well at these different points to see what was the pathway that would kind of like make us somewhat clear on what's going on. And this study was done with like a trickling filter effluent, which is low C2N. So our next phase is going to be using primary effluent and seeing how does these results pan out there as well. So with that, I think that's the end of my presentation, and I think it's a question time.
Fantastic. Thank you both very much for the insightful presentation. Especially in the last part, I think it became very clear how useful high data frequency of liquid phase nitrous oxide measurements is to look into the mechanisms of production. Very, very fascinating work that you're doing. We do have a bunch of questions in the chat, and I will just start with one that is mainly directed to you, Tyler, and was related to your use of compressed air for mixing. The question is, why use compressed gas for mixing in the aeration basin rather than air? Can you elaborate on that? I'm not sure if the question comes through.
Yeah, I guess I'll try to answer it the best I can. We used compressed gas because during our low DO operations, we also have air going into the basin to mix, but it's not enough air per square foot to adequately mix the entire basin. So we add that supplemental mixing in addition to air, using compressed gas in this case, to increase the mixing energy of the basin so that solids don't settle. It's more of a function of the low DO operation, trying to get
Right. Keep
lower
everything in
airflow.
suspension. Great. Okay, thanks for elaborating. And then there's a bunch of questions, mainly for you, Bishav, on the carbon dosing strategies. One is how does the increase in nitrous oxide emissions with micro C correlate to an emission factor? So I think the question is, well, did you calculate the emission factor for your experiments at all? And did you look into stripping in the aerated phases, how much that accounts for?
Yeah, so I'll answer the second question first. We didn't look at the stripping using like an off-gas testing, but using Unisense's stripping equations with Henry's law and all, we saw like a pretty good match between like what we were seeing through our data, like in terms of the actual nitrous oxide profile and the model, whatever Unisense is using, right? So it kind of like suggests it's more stripping rather than like consumption or any other biological activity going on. But that's definitely in our radar in terms of like looking into adding a hood and then looking into measuring the off gas. We're kind of limited with like our SPR is small, it's crowded with like a lot of overhead mixers, sensors, and all. So that's in the next phase. And in terms of the carbon dosing strategy, right now it's not like we're not looking into the NOx value and adding carbon with that. It's more we're adding a fixed volume of carbon using like the control timer. Basically, it's like at the start of each anoxic phase, we're adding the carbon. And the corresponding emission factors with micro C is scary. It's more than 4 or 5. But again, that might be due to like our process not being optimized, right? We might have like a short anoxic time. Like, that's something we don't have the flexibility to change the cycles and all with the current system we have. But like it was higher, like 3 or 4 in terms of the emission factors, 3 or 4%. And with the synthetic formated, it was less than 1. So it was way lower than 1, especially when we're dosing with higher, and higher doesn't mean like way crazy as well. It's like 5 or 6 COD to NOx. We were seeing less than 1 or even 0.5 at times, the emission factors.
So really, really significant differences there.
Yeah, and yeah, we don't want to like rule out micro C as bad because like, our process isn't that anoxic time, right? Like it's really tricky to play with that depending on the loading coming as well. So yeah, we're looking into how do we tackle that as well.
Are you looking into using the nitrous oxides signal for dosing of carbon as well to basically stop overdosing of carbon source?
Not yet, no. Thinking of it, we're exploring that as well, but that's why like I think the first step is to understand what happens when like a lot of these different combinations take place in the reactors. So I think that will inform us in the future.
Another question about the aerated phases. Even though you're not seeing nitrous oxide in the liquid phase during the aerated phase, could you still be producing it and stripping it faster than it's being produced? I'm wondering if you can be 100% confident that you're not producing nitrous oxide during the aerobic phase if you're not measuring in the liquid phase.
Yeah, so yeah, definitely like off-gas testing would be the testing that would validate this, but we did some side checks in terms of we are operating at a low DO, right? So it's like pretty low airflow, and we're looking at that airflow rates and what kind of stripping we might expect in that aeration phase. So definitely there is some stripping going on, but like we don't know that yet, like without doing the off-gas testing. But it's pretty low, so at least you would see some nitrous oxide being accumulated in the liquid phase, which we don't in our system.
Yes, and I mean that gives a clear indication. You actually have a sensor there giving you online values. Great. Last question that we have in the Q&A. Will you be able to share the slides after the webinar?
Yeah, yeah, we will, yeah.
And we do have the clearance, so that's very, very good. Slides will be shared, and also the whole recording will be shared to everyone. So no worries about that. And I'm sure also Bishav and Tyler will be available if more in-depth questions come up, especially Bishav about the carbon dosing experiments. Yeah, I'm sure you can contact him about that.
Sure.
Great. Well, thank you both very much for the presentation and for being available for the questions. I hope you stick around for the last part as well, where I will give some examples from the work that is being done in Europe. Thanks very much. So yeah, to round off the webinar, I would like to bring some European examples of full-scale mitigation and monitoring of nitrous oxide. First of all, just to run through the basics once more. We've heard quite a lot of this already, but just to highlight again that nitrous oxide, I think if you put it boldly, can be seen as an inefficiency of the biological treatment. It's a side product of our nitrogen nitrogen transformations, sorry, in the biological treatment. So whenever the sludge microbiology is seeing sub-ideal conditions, then nitrous oxide can be formed as a side product. And during nitrification, this is mainly a high ammonium turnover that can be a problem, which can be taken care of by adjusting MLSS values. Oxygen limitation can be an issue, so adjusting the oxygen, the aeration strategy is really key for low nitrous oxide operation. And during denitrification, we already heard a lot about the carbon to nitrogen ratio being the most important part. Of course, you can have the well-working denitrification as a very, very efficient sink of nitrous oxide in your process. Generally, what you want to take care of is variations in load and anything that can throw your process out of balance. These will cause higher risk for nitrous oxide. We've already seen also measurements in the standard mainstream biological treatment in the anoxic and in the aerated basins. One other process that I like to highlight now is the side stream treatment, which can also be, well, very interesting to look into the nitrous oxide dynamics. So if you follow me on this diagram, we have, of course, side stream treatment, deammonification type treatment, which is implemented as a quite low energy demanding treatment process, but can have significant nitrous oxide emissions. And why is that the case? Is that you need a perfect balance between ammonium and nitrite to then move on into N2 gas. And if there is an imbalance in your running process, if there's too much nitrite present, then nitrous oxide is being formed. So again, basically a process imbalance, a process inefficiency that is leading to an increase in nitrous oxide production. So here, measuring nitrous oxide in the process and adjusting your aeration and your loading based on that can give you direct information and can enable you to keep the process in balance. Some data from Swiss studies looking into one-step and two-step deammonification type processes We have here again emission factors, which relates to the amount, the percentage of nitrogen that is emitted as nitrous oxide N. In one-step processes, they've measured emission factors between 2 and 4, whereas two-step processes, they have measured emission factors up to 20% of the total nitrogen. So this is very, very significant, and obviously something that operators of such processes want to have under control and look more into. One such study where optimization of a side stream reactor has been done is this one from VCS in Denmark. They've had two reactors, one control reactor, which was operated under the standard nitride-based intermittent aeration, and then a nitrous oxide-based control. Initially, and the most practically effective one was a continuous aeration where the airflow was based on ammonium in the effluent, and then a cycle time as well as a loading of the reactor based on nitrous oxide in the feedback loop with an online sensor. And they have shown over this testing period that 50% less nitrous oxide has been formed with this operational strategy, as well as a lower energy consumption. Another type of strategy has been modeled in this work, which was intermittent aeration with a minimum baseline aeration and then superimposed alternating aeration, again based on nitrous oxide as the triggering factor. But in this case, the blowers that were in this reactor were too large to actually get this fine tuning down to the right level. So this is something to take into account when optimizing your process. Of course, the equipment on site needs to be able to deliver that fine-tuned air as well. Another reduction example from Denmark is shown here in this work. This is a medium-sized treatment plant for Danish type of sizes, taking care of wastewater of about 50,000 people. And in this study, a controller based on ammonium, nitrate, and nitrous oxide has been applied to reach SND process and optimize the process in this way by having a stable SND running. And what they reached in the operational tank compared to the process tank was a reduction of almost 50%, 46% less nitrous oxide, while there was a slightly higher energy consumption in this operational mode, but also a significant increase in the capacity of the reactor. So in this case, in case of Skanderborg, this is very important because they have a large influx of people due to an annual festival. And I think this is relatable for many other operators of wastewater treatment, that you have these changes throughout the year. So here, really a very strong benefit that can be gained. The next point I want to go into, there have already been a couple of questions on the webinar about comparing liquid phase measurements with airflow measurements, and these questions are certainly coming up a lot, which is why we are looking into the comparison of the methods, of course, very much in depth. Here, first of all, I am showing some older data, which is pointing into the direction that the placement of a hood is very, very important for the amount of airflow that you're measuring, and therefore the emissions that you're going to report. Basically, what we see on this small graph here is that using the same airflow from the hood and then calculating the emissions based on the process sensor, on the liquid phase sensor and the hood, you get a very similar result. Whereas if you use the tank airflow, you're getting a much lower result, which points to the fact that you're overestimating based on placing your hood in an extremely high flow zone. Basically, we can all know from walking a wastewater treatment plant how inhomogeneous the surface of a treatment plant can be, and therefore how difficult it is to catch an airflow that is representative. So for that reason, the liquid phase sensor and emission calculation methodology is always based on the full tank airflow, which makes sure that the stripping is based on that calculation, all the air going through, taking all the nitrous oxide at the applicable rate based on the model. And if you want to sample with airflow hoods, a comparable reasoning can be from the American Society of Civil Engineers standard. There it is stated that 2% of a basin's total surface area needs to be sampled in order to give a representative value for air going out of the process, in this case oxygen testing. So this means a lot of different places for measurement, and similar work is actually being done. So this is what we like to present in the next slide, is some very preliminary data on this ongoing project, again in Denmark, where the Danish ministry is funding this work, and 8 hoods are being compared directly with 8 liquid phase sensors in order to find out if, well, first of all, if they are comparable, but also whether one position is representative for the full tank. For the liquid phase sensors, this is the data that is being shown on the left here. We can quite easily say, yes, in this reactor, the 8 sensors are following each other perfectly, and thus you can have one position measuring, giving you a representative value, both in liquid phase concentration and then calculated emission for the whole tank. So this is the preliminary results from here. More results from this N2O mobile project will of course be shared as soon as the project is concluding, and yeah, we're very much looking forward to see this data. One further validation study that I would like to present is looking at the comparison between in situ measurements, so liquid phase sensor, versus remote sensing, and here specifically highlighting the drone flux measurement as a very good methodology to validate your full plant emission modeling. This is what is shown in this study, again sponsored by the Danish Ministry of Environment. We have a comparison of these 3 methods, and overall as a summary of the data, showing that the average emissions per hour are in a very similar type of range between the 3 methods during the comparative period, and the total emission factors that are being calculated based on the different methods are also highly similar. So while these methods are of course giving a snapshot only, a one-time measurement of the emissions, they are very, very useful in giving a validation of the emission and cross-checking what you are calculating based on the in situ measurements, which are actually used to monitor the process. Yeah, with that, I reached the end of my presentation. Just like to highlight a few points of the nitrous oxide process sensor. We are working with more than 300 utilities around the world, and the sensor is also applied in nationwide nitrous oxide monitoring campaigns in several countries. The measurement precision is proven and featured in scientific articles, so there's ongoing validation. We are very much keen on working with scientists worldwide, staying true to the roots of Unisense as well, and making sure that our data is validated. And then I think through the other presentations, it also became clear that the liquid phase measurements is giving unique advantages for calibrating models, for building digital twins, and also mainly for online process optimizations. And with that, I'm at the end of my presentation. I'd like to welcome any questions that are still there. Let me just see if there's any questions coming in to the chat. So there's one question around reliability of the ammonium sensors in relating to the deammonification study, how reliable they are, and whether the nitrous oxide sensor is feeding into the PID loop together with the ammonia value. Since I haven't been part of the study, we'll have to get back on that question via email afterwards, but we'll make sure to do that. And then there's a question about the hoods being used in the N2O mobile project. These are coming from Upwater in Switzerland, and we're very, very happy to work closely with them in this project, along with the other project partners. And yeah, so that's the company supplying the hoods for this work. If there are no other questions, I think we can all give each other another a 5-minute break before the next meeting, and enjoy that gift of extra time. I would like to thank again all the speakers for their preparation, for their time today. All of you, of course, for being interested in the topic, and for following us in this work. Do make sure to come by at WEFTEC if you're around, and well, I look forward to being in touch with you. We will follow up by email on all the questions that were still there, and we'll be in touch with you separately on that. So thanks very much, everyone, and have a lovely rest of your day. If you like to just turn on the cameras for one last round, you're welcome to do that, so we can see that we have done this webinar with actual people. We've had more than 100 people, 150 people signed up, being on the call, which is a really great turnout. And then all the others will get the recordings and can watch it at their own leisure. So yeah, thanks a lot to all of you, and look forward to the next work together. Cheers.